Hello, and welcome to the third episode of my webinar on textual data processing with large language models, or LLMs, in the humanities. In the previous episodes, we focused on information extraction and data transformations. In this episode, we will continue with a specific type of transformation. This transformation produces mathematical objects, named vectors, to represent words and texts. We can use these vectors to study, for example, the meaning of words. The use of vector space representation in textual scholarship and beyond had been invented well before the arrival of artificial intelligence. However, as I will explain today, the recent advancement in generative AI gave an enormous boost to this representation and its use for text analysis. Now, let's cut to the chase, and let's try to understand how the meaning of words and vectors are connected with each other. To understand this connection, we need to take a longer journey and talk about the abstract concept of word meaning. First, let me ask a somewhat challenging question. What is the meaning of a word? I'm quite sure that hearing this question you think about dictionaries and encyclopedias. If you want to understand the meaning of a word, you simply open a dictionary and check the definition of that word. But intuitively, we feel that we understand a given word not because we have a clear definition of that word. A definition does not cover the entire usage of a word. Linguists and philosophers, such as Ludwig Wittgenstein and Ferdinand de Saussure at the beginning of the 20th century, recognized the problem. The meaning of a word cannot be based on a simple definition. Instead, Wittgenstein suggested that the meaning of a word lies in the way the word is used. Others, such as Saussure, complemented Wittgenstein's idea of meaning, taking it as simple as possible. The meaning of a word lies in the way the word is related to other words, or the way it is used. The linguist John Rupert first famously said, "You shall know a word by the company it keeps." To put it in another way, the meaning of a word depends on the context in which it is used and the other words that they typically accompany it. To make this idea more intuitive, let's resolve a small puzzle. The British government has a mysterious civil servant named Larry. He has been incumbent since 2011. He reports directly to the Prime Minister. So who is Larry and what is his job? To answer this question, let me show the typical words accompanying Larry. So the words that typically occur with Larry are the following ones: male, fur, whisker, feline, and so on. So what is Larry and who is Larry? Larry is a cat. He is the current chief mouser to the Cabinet Office. He lives and works at the Down Street, and his job is to catch mice. The example of Larry demonstrates how words typically co-occurring with a given word define the meaning of that word. When we work with vector space representation of words, we rely on this definition of meaning. Let's examine what this implies in practice. Imagine that we have a language consisting of only three verbs: purr, bark, swim. We use this language to write three sentences. Larry is purring. Commander, who is the dog of Joe Biden, is swimming. And Commander is barking. What is the meaning of Larry? What is the meaning of Commander? You can visualize their meaning as follows. We can imagine the imaginary language as a simple three-dimensional space. The three words are the dimensions. So on the plot you can see three axes corresponding to the three verbs. Notice that Larry and Commander are different points in this space. For the sake of clarity, I added a third animal to the list, and this is Rosa Luxemburg. Not the famous philosopher, but the former tortoise of Balliol College, Oxford. And here is a sentence with Rosa Luxemburg. Rosa Luxemburg is swimming. The three animals are three different points in the space that has three dimensions. We can also imagine this as follows. The 3 points representing the 3 animals are actually vectors. Vectors are different from points since they have 2 additional features, length or magnitude and angle. These additional features are very useful because they can support the meaning. For instance, to see how close the meaning of 2 different words are, we can simply calculate the angle between their vectors. The smaller the angle, the more closer they are semantically to each other. Synonyms have more or less the same vectors. In this toy example, we can see that semantically Rose and Commander are closer to each other than to Larry. They share the word swimming that accompany both of them. By contrast, Commander and Larry do not share any words. The example given is only an illustration. Of course, in reality, in a language, there are tens of thousands of words. Hence, when we work with vector space representation, we do not use a 3-dimensional, but a high-dimensional space. Then, we do calculations on words represented by high-dimensional vectors. On the slide, you can see the simplified procedure we apply. First, we process a very large textual corpus and learning how words are related to each other. In practice, we build a table or a matrix, like the one on the previous slide. Each row representing a word is as a vector. Columns are the other words. Second, we quantify the relationship between words. In the toy example, we just counted how many times a word co-occurs with another word. In reality, we use more complicated metrics. The result is that for each word, we have a vector representing the meaning of that word. Again, meaning is defined through the words that surround a given word. This is encoded into the word vector. With AI, this procedure is changing and becoming more powerful because of the following reasons. You can submit directly your text to AI that is capable to obtain the vector space representation of each word without the need for preprocessing. AI does not use the traditional vector space where each word is a different dimension. In short, when an AI model is trained, it learns the word vectors on a gigantic amount of data. Then it creates an optimized vector space. When you submit your text to AI, then it uses this optimized vector space and creates specific word vectors accordingly. These specific word vectors are called embeddings. These embeddings are very powerful because they are based on billions of different documents. You can use them to investigate, for instance, semantic similarity. Finally, with AI we can obtain the vector space representation of not only words, but also entire paragraphs or longer texts. Let's see how the vector space representation of text looks like in practice. On this slide, you can see short documents represented through vectors. The documents were submitted to ChatGPT, which returned a vector space representation of the documents. Originally, these vectors had several hundred dimensions. In other words, the underlying space was a high-dimensional space. For visualization purposes, I projected this high-dimensional space into a 2-dimensional space. Now, we can use the visualization to observe clusters of similar documents. For instance, the highlighted documents all revolve around the theme of celebration. They are semantically close to each other. Hence, they are also in close proximity in the document space visualized by the plot. I'm hoping that now you have a basic understanding of how word and text vectors work. Next, let's see how they are used in real life for different purposes. We have already talked about one use case. This is the study of word meanings and generally semantics. With vector space models, you can analyze how the meaning of a given word was changing over centuries. You can gather insights into how a new meaning rose and the old meaning became obsolete. But there are other important use cases. Semantic search and information retrieval are other use cases. And I'm sure you have already experienced the need for a semantic search. Let me highlight this need through a personal example. I'm a historian of Nazi persecutions. I often use Google to search for documents related to the Holocaust. For instance, if I search for women history, I enter the search terms Holocaust plus women. With these search terms, I find documents explicitly mentioning women and the Holocaust. Nevertheless, documents where the terms Shoah and women occur are not retrieved. The reason is that the traditional Google search engine does not know that Shoah and the Holocaust are synonyms. And this is where the strength of semantic search engine comes from. It is able to find not only the search terms but also their synonyms. Question and answer systems present a similar use case. You can train an AI model on a large corpus of texts. This is called fine-tuning. Then you can use a chatbot to ask questions and find relevant answers based on the input corpus. The fluent conversation between you, the chatbot, and the input corpus is enabled by the vector space model of words and texts. Another example where vector space models has a crucial role is recommendation systems. You go to a library catalog and you look for a book about a specific topic. Then suddenly, the catalog invites you to check similar books as well. How does the system know that these books are similar? Most probably, all book abstracts were transformed into vectors. Then, the system uses these vectors to find clusters of similar books, which are then offered to the user. To summarize, vector space representation is based on the idea that the meaning of a word lies in the relationship it keeps with other words. When working with word vectors, we use a representation that encapsulates all relations a word has, including the strength of these relations. Since vectors are mathematical objects, computers can easily work with them. Most importantly, AI-empowered word and text vectors can help explore meaning and similarity based on a very large amount of data. I would like to thank you for attending this webinar. I'm hoping that I've managed to showcase the power of generative AI for research in the humanities and beyond. I look forward to welcoming you to more of my webinars in the future. Thank you very much.